Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at networks, specifically their nodes and edges. So networks are basically just collections of these things called nodes or vertices. They mean the same thing. And the things connecting them called edges. So the nodes and edges can represent anything. There's heaps of areas in the real world in which they are used. So for example, each node could represent a city and each edge could represent a road that connects them. For something like this, which we'll see as a directed graph, it could model water flow. This could be like the source of water, like a lake or something. This could be different reservoirs. We'd call this the sink, whatever. Networks are also used in contact tracing to see who's infected who with an infectious disease like COVID. They're also used in mapping social networks. They're used in many different areas of mathematics. All we're really needing to get out of this video are some definitions. So let's look at this one here. So this is called a connected graph. Now note that network and graph can be used interchangeably. I know it's confusing that mathematicians often use different words to represent the same thing, but just note graphs and networks are the exact same thing. So the reason this graph here is connected is it's possible to go from any vertex or node to any other node. That, however, is not possible in this one. If you're at vertex G, for example, you can't get to some of the others. Because these edges have directions on them, if you're in vertex J, you can't get to any of the other vertices. So that's why this graph is unconnected, whereas this one was connected. So this one is an undirected graph. What that means is there's no direction, no arrow along the edges. It means that travel is possible in both directions. You can go from A to B or B to A. On the other hand, this is a directed graph because each edge has an arrow. You can only go in one direction along each edge. For example, you can only go F to I, not I to F. Now, sometimes you will see numbers on edges in a network. We call those weighted graphs. Each of these numbers is a weight, and they're very important. They could represent something like distance between towns. They could represent the cost of cabling, whatever. Sometimes they will have them, in which case they're weighted graphs. Sometimes there will be no numbers on the edges. They're unweighted graphs. So this here is a graph that has 1, 2, 3, 4 vertices or nodes. Remember, vertices and nodes are the same thing. It has 1, 2, 3, 4, 5 edges, whereas this directed graph over here, 1, 2, 3, 4, 5, 6 vertices or nodes, and it has 7, 1, 2, 3, 4, 5, 6, 7 edges. Now, a couple more definitions that are important. This graph here contains a loop. A loop is this thing here. It is an edge from a vertex to itself. It also contains what's known as a cycle. So a cycle is a path from, well, it can go through as many vertices as you like that starts and ends at the same vertex. So for example, we can start at B and go on a path through other vertices back to B. So this graph does not have any loops. It has no nodes that connect to themselves through an edge. It also has no cycles. So one other thing that is very important in definitions is this notion of the degree of a vertex. That'll become especially important when we look at Eulerian and Hamiltonian paths. So what do I mean by the degree of a vertex? Well, it's actually pretty simple. It's just how many edges connect to that node or vertex. So for example, if we look at this graph here, we have that the degree, so we'll just call it deg A, degree of A is 1. There is only one edge that connects to A, whereas you can see for something like D, its degree is actually 4. That probably sounds a bit counterintuitive, but there is 1, 2, and we count the loop as 2. Its degree is 4, so there are like 4 edges, or 4 ways you can get out of D. You can go this way, or this way, this way, or this way. So the degree of vertices in a graph like this, a directed graph, is a bit more complicated. There's actually an in degree and an out degree, but we won't go through that in this video. Instead, let's look at solving a problem where we would use a network. So here I've come up with a table that shows the cost of travel from each of these suburbs to one of 5 suburbs. So let's go ahead and draw a diagram to represent this. So each of the 5 suburbs will be a node or a vertex. So let's start with L. So Lyneham, we know, connects with Dickson, O'Connor and Watson. O'Connor and Dickson also connect to each other. So what we might do is put O here and D here. So they have a little cycle going on. Now of these, only O'Connor connects with the city. So I'll put it down here. Now Watson, on the other hand, connects with all of them. So I can put Watson over here. So we have our 5 vertices. Let's now draw the edges. So we know that Lyneham connects to Dickson. It also connects to O'Connor. Now it might look hard to connect Lyneham to Watson, but you can draw an edge like that. That's absolutely fine in a network. So let's put on the amounts. So Lyneham to Dickson and Lyneham to O'Connor are $3 each. Lyneham to Watson is $5. Now let's look at Dickson. So Dickson connects to O'Connor, so we'll put that there, and that was $6. And of course Dickson connects to Watson for $2. Now we look at O'Connor. So O'Connor also connects to the city for $4 and $3 to Watson. And now we connect Watson to the city for $1. So the kind of question you might be asked is, what is the cheapest way to go from Lyneham to the city? So there are lots of different paths we can take here. We're going to look more formally at how to do this in subsequent lessons, but for now we're just getting used to the idea of weighted graphs. So there are lots of different paths I could take. I could go Lyneham, O'Connor, city, that would be $7. I could go Lyneham, Dickson, O'Connor, the city, well that's going to be pretty expensive. Hopefully, eventually we can see that the cheapest way is to go from Lyneham to Watson for $5 to the city for $1. $6 is the cheapest. All right, time to now look at a few more definitions. So we need to be a bit careful with the definitions here because different textbooks define these concepts slightly differently. Pretty much every textbook agrees that a walk is just any sequence of edges that's traversed. It's basically just a journey. It's just where you start at one vertex and end at another. So A, B, C, that's a walk. But textbooks don't always agree as to the definition of trail and path. For our purposes, we're going to say a trail is a walk that uses a different edge each time, and a path uses a different vertex each time. Some textbooks say that a path is a type of trail. Some say it's not necessarily a type of trail. But for our purposes, we're not going to delve into that. Now, a circuit is just a path, so it needs to use a different vertex each time, except that it starts and ends at the vertex. So it's a bit confusing, so let's go through some examples. So A, B, C, B, A. This is how we define like a journey. We go A to B to C, back to B, and to A. So this is an example of a walk. It is not a trail because we went along these edges more than once. It's not a path because we visited vertex B and also vertex A more than once. Now, because it's not a path, it can't be a circuit. So let's look at this next one. We go A, B, C, F, D, C, E. So here we haven't used the same edge more than once. So this is an example of a trail. It's not a path, and the reason is we visited vertex C more than once. Let's look at this one. So we can go A, B, C, E, F, D. This is a path. You can see that we didn't visit any vertex more than once. It's also a trail because we didn't go along any edge more than once. It's not a circuit, however, because we started at A and ended at D. We didn't start and end at the same vertex. So for this last one, that's the same path except we go back to A. So A, B, C, E, F, D, A. So it's just like a path because we didn't visit any other vertex more than once. And it's a trail because we didn't go along any edge more than once. So when we have a circuit, it's okay if you visit one vertex at the start and the end. That's okay. It still qualifies for a circuit. All right, let's now look at planar graphs. So planar graphs have the very appealing property that you can draw them without any intersecting edges. This may be very useful in something like drawing a road network and you don't want any roads to intersect. So this is an example of a planar graph because it has no intersecting edges. So it turns out in any planar graph, Euler's formula, this formula up here, is satisfied. It says the number of vertices minus the number of edges plus the number of faces is equal to 2. So for the faces of this graph, it's all the ones enclosed by edges, but we also have to include the outside of this. So this actually has 3 faces. So we can see the number of vertices minus the number of edges plus the number of faces does in fact equal 2. So Euler's formula is satisfied. Now this here may look like it's not a planar graph because it has intersecting edges, these two here, but we can easily redraw it without intersecting edges. So here I've drawn 5 of the edges. I need to connect B to C, so I can't do it through here because they would intersect, but I can draw an edge that goes around here. These two graphs are said to be isomorphic. That basically means they're the same. It means I've got the same number of vertices, same edges, each edge has the same degree, etc. These two are isomorphic. This is clearly a planar graph. Its faces, it has 1, 2, this is a face enclosed by the edge there, and again we can't forget to include the outside. So here this graph has 4 vertices once again, it has 6 edges, it has 4 faces, and of course 4 plus 4 minus 6 does equal 2. Euler's formula is always satisfied for a connected planar graph. So just a little more on being isomorphic. I just want to point out that these two graphs here are not isomorphic. Yes, they both have 5 vertices. Yes, they have, connections from A to B and A to C, but you can see clearly this has more edges. I mean, if you just look, the degree of A here is 1, 2, 3, 4. The degree of A here is only 2. So even though these look the same, because they don't have quite the same connections, they're not isomorphic. They're not exactly the same. This is not a planar graph. You can't redraw this without intersecting edges. On the other hand, this is a planar graph. So it has 1, 2, 3, 4 faces. It has 5 vertices, and we can easily count that the number of edges, 3, 4, 5, 6, 7. So because it's planar, we'll have that the number of vertices minus the number of edges plus the number of faces is equal to 2. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.